Alright, so here's our introduction to talking about energy, work, and power. So you've definitely heard of kinetic and potential energy, but when we talk about doing work, it means something specific. So I'd like you to consider two examples. And so the first example is a student is sitting here holding a book, okay? And you can imagine them holding 10 books, or holding the book, so here's them, here's the book, holding the book so that their arms are outstretched. And after a while, they're going to get tired. And so this student is going to feel like, wow, I'm really having to exert some force to hold the book up, which is true, and wow, I'm getting tired because I'm working so hard. But you can have a table doing the exact same thing, meaning holding a book completely stationary, and the table is going to do that for free. You don't have to plug the table in, you don't have to put gas in the table doesn't have batteries. The table is just going to hold that book up for hundreds of years without requiring any energy to do it. So this person, technically speaking, isn't doing any work because some inanimate object that doesn't require energy can do the same thing. We can consider a person holding books and moving to the side, and it ends up being the same thing. So here's the person. These drawings are just looking awful. Sorry. So here's, well, at least give the person a smiley face. Okay. So they're very happy to participate in the physics experiment, and this person is going to walk this way, and they're not changing the elevation of the book, but they're moving to the side. And they're like, wow, I'm really working hard because not only am I holding this book up with my arms straight, but I'm walking to the side, and I'm going to walk across a football field, holding this book straight out, and I feel like I'm doing so much work. But then you imagine a frictionless, and I know it's like, oh, that doesn't really exist, but we can get pretty frictionless if we try. So you imagine this frictionless cart. It's like a table, and there's this perfectly smooth, flat surface, and the cart is already moving, and it has the book on it. That cart is going to continue to move, of course, neglecting air resistance. It's frictionless, but it's going to continue to move to the side. Its own momentum carries it, right? Objects in motion tend to stay in uniform straight line motion, and so we could say it does the same thing without requiring any energy, without requiring some form of input. And I think you know what I mean by energy, and we'll talk about the definition, but the cart's going to do the same thing. So this poor human that's walking across the football field carrying the book straight out is actually doing no work, even though they feel like it. So the question is, well, what does it actually mean to do work then? And we'll talk about that right here. So if the person were to, so here's Joey, our textbook holder. If the person, and that's their weird book, if the person were to lift the book, that would all of a sudden, so they're moving it through some distance and they're having to exert some force. So there's the force, and here's their movement. Then, yes, they did work, because a table or a roller cart is not going to be able to do that. It's not going to be able to lift the object against the force of gravity without some energy input. You have to plug it in, it needs batteries, you wind it up, there's a spring inside it, something like that. So yes, did work, and so we're going to say energy required. And so before I turn the page, because I won't be able to come back to this, the definition ends up being that a force is exerted in the direction of motion. So here the book is lifted up, and so the force is exerted in the direction of motion. However, in these previous two examples, so over here, the force was exerted but there was no motion. And in this example, the force Joey was exerting was in this direction but perpendicular to the direction of motion. So there's motion and there's force. So because the force did not have any component in the direction of motion, no work was done. And the table, the inanimate object, not requiring energy, could do that for free. So let's look at page 2 and talk about so that's just our example. So here's what we say. If you exert a force through some distance, meaning some part of the force is in the direction of motion, then you do work. And work can be sort of described as expending energy. It takes energy to do work. Work and energy are measured both in joules, and so in chemistry we talk about calories or kilocalories, and we'll relate the two, but joules is definitely the physics unit for energy. And here's a definition. So this says that work is equal to force times distance. And you can keep that in mind, and that will suffice, force times distance, as long as you understand that the force has to be in the direction of motion. So if we look at a formula page, it's going to say something like force times distance times cosine of theta, or force parallel to distance, meaning the component of force parallel to the distance through which the force moves. So here's an example. We have some cart and we're pulling it along, or a crate, and we're pulling it along the floor, and we pull it through a distance of 5 meters. So we're definitely exerting some force. This force is not directly in the direction of motion. If the force were like this, so hopefully I'll be able to erase this. If we're 100 newtons and it's moving in this direction, we could just say that the work is equal to the force times distance, and that would be 100 Newton force times 5 meters, giving us 500 joules. And so we're seeing here that a joule is equal to a Newton, a force of Newton exerted through a distance of 1 meter. If the force, however, is at some angle, so here's our SOHCAHTOA stuff, which you love so much. So this force is pulling to the right and up, and it's only the force being pulled to the right that's actually going to do work through that distance. So we would say something like 100 cos of 20 degrees, and that's equal to the force exerted, and we would then multiply that by 5 meters to get the work. Because, sorry my voice is so raspy, because it's only the parallel component of force that's in the direction of motion in this case. Okay, so a lot of blank space on these notes. Here's an example. So we have a hiker and she is going uphill, and it's on some weird path, right? She's moving to the sides, she's moving up, she's moving up, she's moving to the side. But when we go to figure out how much work she actually does in carrying the backpack, so 20 kilograms, that's like 45 pounds, 50-pound pack, so that's pretty heavy. Yeah, closer to 45. Technically the only work she does, right, moving to the side, she's not doing work, but moving up against the force due to gravity, then she is. So what we would do is we could say that the work done is equal to the force times the distance, and the force that she exerts on the backpack to lift it is equal to its weight. So W equals mg, and that would be 20 times 9.8. So the force that she has to exert just to hold the backpack steady is 196 newtons. And if she's moving the backpack upwards at a constant speed, that's the force she would exert as well. As long as the backpack isn't accelerating upward, the force would not be greater. So the distance in meters is 1,000 meters, and the force exerted is 196 newtons. And so she's going to exert, and I think we have 1.96 times 10 to the 5th, and that would be joules. So if we compare, let's see, I think I have some conversions. So it turns out that 4.184 joules is equal to 1 calorie. And when we talk about food calories, it's actually a kilocalorie. So we could take these numbers if you're like, hey, how much does she have to eat to fuel her to the top of that mountain? So we could take this, joules, we could convert it to calories and kilocalories, and then into Snickers bars or donuts or whatever. Okay, so that's an example. The force that she has to exert is in the upward direction to lift and carry the backpack, and so we're only interested in the direction she went up and not the direction she went sideways, or the distance, excuse me. Alright, so you've definitely heard about the difference between potential and kinetic energy, and if you look at the physics definition of energy, it's described as the ability or capacity to do work, and if we look at work, it's defined as the energy exerted in moving against a force or something like that. So the definitions are kind of cyclical, where one is based off the other and the other is based off the other. But you can think about work done as, let me write this for you, is exerting a force through some distance. So we're talking about work here, force through some distance. And so when we talk about energy, we're talking about something that enables us to exert a force through some distance. So you've heard about kinetic and potential energy. And when we talk about kinetic, we're talking about movement. And so kinetic energy is energy of motion. So anything that has motion or velocity and mass is going to have kinetic energy. Here's our formula for kinetic energy. So let's write these out. This is kinetic energy, the energy of motion, and it's 1/2 the mass times the velocity squared. And because you end up squaring it, the positive, we don't talk about a positive or negative kinetic energy. It's going to be some positive quantity no matter what direction it's moving in. And so I don't even know what he is saying down there. Ape? I don't get it. So here we have a big boulder that's rolling towards this poor human that's saying something weird. But if we were finding the kinetic energy of the big boulder, so it's 200 kilograms, so we'd say 1/2 and then mass, and then times velocity squared, so it'd be 15 squared, and 115 squared, 225 with 2 zeros, so something like that in terms of joules. Okay, kinetic energy, energy of motion. And you probably learned in this situation, the boulder up top, right, as it's at the top of the hill, it has some potential energy because it has some height potential, meaning the ability to speed up and gain kinetic energy. So that's probably on the next page. All right, so before we move on to potential energy, let's talk about the difference between just talking about the work done in an object and the net work being done in an object. So if we look at our first situation, the box has a mass of 10 kilograms and so a weight of 98 newtons. And if this person lifts the box 5 meters up, so that's like 15 feet, so they're carrying it up to the second story, we could say that the work done by person is equal to the force times the distance. So they're not speeding it up, they're just exerting a force equal to its weight. And what is that? It's going to be 10 minus 500, or 10 less. Okay, so 490, and this is energy or work, so it'd be joules. All right. And so notice how the force that they're exerting is in this direction, and the direction of motion is in this direction. So we can say this is motion. So that's the force that the work done by the person. But this box has more than one force acting on it. So we have the lift by the person, but we also have weight. So gravity's pulling down. So we can also talk about the work done by gravity. And that's kind of easier to understand when something's falling because gravity's pulling it downward and it's moving downward. But in this case, we have this force due to gravity that is directly opposite the direction of motion. And so because they're in opposite directions, the work ends up taking on a negative value. So we can say that the force is downward, so negative 98 newtons. This is for gravity. times 5. And so this would be negative 490 newtons. So if we're talking about the net work done on an object, we have to talk about the work done by the person and the work done by gravity. So because this thing didn't speed up, the net work done is actually equal to 0. And so I know that's a little weird, but this is really helpful in sort of helping that make sense as this material becomes more familiar to you. So the change in kinetic energy is going to be the net work done in an object. So if we have this situation off to the right where a person is lifting an object, but they're lifting with a force that is greater than the weight, it will be speeding up. So let's take a look. We have a force upwards of 198 newtons. So that's just the person lifting. And the force downwards is 98 newtons. That's the weight. So we could say that the net force acting on the object in this case is 100 newtons. And the net work done on the object is going to be the net force times the distance. So I'll write that net work equals net force times distance. And so we get 100 newtons times a distance of 5 meters, giving us 500 joules. And that would be equal to how much the kinetic energy has increased by. So the kinetic energy would have sped up or increased. You wouldn't say the kinetic energy has sped up, sorry. Kinetic energy is increased by 500 joules. And so if we were to go through a calculation where we figured out this mass, this force, that acceleration through that distance, and then found the velocity, and then did 1/2 mv squared, we'd end up with 500 for the increase in kinetic energy. So it's kind of like a shortcut when figuring out acceleration and velocity is difficult. Okay, on this next page we're going to wait for part 2. Let me just say, so when we talk about potential energy, we're usually talking about gravitational potential energy, and we're going to use the simplified formula just like mgh, or change in height. But we can also talk about gravitational potential energy for something that's far away from a planet. We could talk about chemical potential energy when you put gas into a car and the gasoline burns or explodes. We can talk about, this is like spring potential energy, so on the trampolines at Snow Creek, or elastic potential energy. So a bow and arrow, when it bends, there's actually elastic potential energy in here. So you release it and the arrow moves forward fast, picking up kinetic energy. Okay, so that's it for part 1. We'll continue part 2 soon.